today I'm going to talk about gRPC and Kubernetes. A bit of background on me, I guess we've already covered this, but yeah, I used to work on Kubernetes and Prometheus at a company called Weaveworks. Before that, I worked at Google on Google Analytics. Before that, I had my own startup. And I like to brew beer. And right now, I'm working on Prometheus, which is a monitoring system. It was a second project accepted into the CNCF after Kubernetes. And so I'm a Prometheus developer, and I've got a little startup where we run a hosted version of Prometheus. But I'm not really going to talk much more about that. So, a bit of audience participation. I like to get everyone's blood flowing in the morning. So, everyone get your hand up. This is not optional. Everyone. I'm checking. There's a guy. Yep. Get your hand up in the back. Good. Right now, if you're a front-end... no, keep them up. If you're a front-end developer, and only a front-end developer, you can put your hand down. Good, so mostly back-end. Okay, now if you only do back-end, you can put your hand down. So most of you are full stack. Interesting. Okay, good to know. Who here, you can put all your hands down now. Who here mainly codes in Golang, or has done any coding in Golang? Oh, more than I was expecting. Good. Well, the talk's mainly going to be written in Golang because that's what I've been coding in for the past 3 years. But it's very language agnostic. So the talk is based on a previous talk I gave about how we use gRPC at Weaveworks, and I've kind of evolved it to be a bit more generic. But the experience comes from using gRPC and basically plumbing it through all of Weaveworks services and changing from a RESTful HTTP model to gRPC. It's going to be 4 bits, although I imagine we probably won't have time for the last bit. We're going to cover a really basic introduction to what gRPC is, a bit of history, and how to use it. Then we've got a bit of a worked example. And then we're going to get into some more interesting stuff that I've learned from actually using gRPC in anger for the last kind of 18 months. If you've got any questions, please just dive in, in the middle of the talk. I'm glad you could join us, Matt. What time do you call this? So, straight in. Who here has had to write code like this? This is, in Go, your kind of standard hello world, marshalling JSON, doing a HTTP handler. Who here's done that? Yeah? I mean, that's a lot of code to basically just say hello. It's about 120 lines of code, if all compiled into a binary. And this is kind of circa, early 2000s, this is how you would build a web service. You would have some structures, which are these things up here. You would marshal them into JSON. You would respond, and then you'd marshal it back into JSON. And in your client, you would have to do that all again. And you'd have to do this for every single language you wanted to support. So if you're a web service and you're publishing an API, developers don't like to just do this themselves. They want a client library. So you've got to go through and you've got to write 10 different client libraries in 10 different languages, and you've got to maintain them, and you've got to do this for every HTTP handler, and it gets kind of painful. The other problem here is there's no real formal definition of your API. You haven't kind of sat down and said, this is what the API supports. You haven't said, this is the types it accepts. And you're kind of hamstrung by JSON's type system, which is, as we all know, not particularly good. When you decide, sending raw JSON over the wire is not that good, I really should layer on some compression, let's say, you've got to go through and manually put into your servers the compression handling, and then you've got to deal with backwards compatibility. And let's say you want to deal with MIME types and you want to give HTML to the browser and it just gets really complicated. And then you decide, what I really want to do is I really want to do like an interactive web client that supports like server-side push. Yeah, now you're finished. You can't really do that. So, gRPC is here to stop you from doing this and to save you from having to do this. gRPC is a high-performance, open-source, universal RPC framework. So this isn't a new thing. They've had these for about 30 years. But gRPC is the newest and greatest one. You write your interface definition once, so your interface definition looks a bit like this. And then gRPC compiler will generate you server-side and client-side stubs for about 10, 11 different languages. So let's quickly walk through this. We have some types. They look a lot like the Golang types we were describing before. They call them messages. And you have to number the fields. And the field numbering is there for forward and backwards compatibility. So this is one of the things you get for free. So you say, I've got a request, it takes a name. I've got a reply, it gives you a message. And then you say, I'm going to wrap this all up in an interface which takes a request, returns a reply. We give it some metadata saying what the name of the package is, and you should all be using Proto 3. And then you run the command line and it generates you the language stubs you need. So now let's go through a bit of history, because as I said, in computer science, nothing is ever new. This all kind of started with Corba in the early 90s. So Corba was a definition for kind of really enterprisey RPC frameworks, but it had the same kind of premise. You'd write down the interface definition, then the Corba compiler would generate you stubs for, at the time in 91, it was only C++, I think. Maybe it was C. But as this evolved, Corba started to support Java and other languages, but it was a binary format. It used its own transportation layer. It was really complicated, and it was really hamstrung by poor implementations. And so it went from being the new hotness in the beginning of the 90s to universally hated up 10 years later. About the same time, the web was starting to become a thing. Java was starting to become a thing. So Java had its own take on RMI. So this was where you would build a Java interface. You could put some annotations on it, and then Java itself would go away and generate you the client and server-side stubs. Unfortunately, it was all very Java-y, and so it didn't really have the cross-language support that you need in this kind of system. And of course, as the web was the new fashion, we had to use XML, we had to use HTTP, and so SOAP came along, and SOAP was, again, the same thing. You write down an interface definition, this time in very, very verbose XML. You use the SOAP compilers to generate you, well, actually, the interface definition would be in WSDL, which stands for Web Services Definition Language. You would use the SOAP compilers to generate you bindings, and then you would run, HTTP and XML transactions back and forth. And it was really wordy, and it was really, really complicated, and it had support for every single mode of operation you could possibly imagine. And kind of, I think, in the early 2000s, developers had had enough. These systems before were complicated, were buggy, were really verbose, were really poor performing. And so there was the manifesto that came out, I think it was a chap's doctoral thesis, basically saying, look, why are we doing it like this? We should just use HTTP and JSON, and we should just represent the structure of our API in the URL. And this was really good. This probably is still the fashion. I think the chap after me is going to talk about that kind of API. At the same time, in the background, Google was a thing. Internally, Google decided they didn't want to go that route. They still wanted to go the kind of IDLs with auto-generated code and really based on RPCs, and they had a thing internally called Stubby. This has not been open source, but they do talk about it. And Stubby was built on an encoding library called protocol buffers. Now, this is something Google has open sourced. They open sourced it in 2008, and this is Google's internal system for describing a structure and then serializing it as ones and zeros. And it's got all sorts of fantastic things like backwards compatibility. It has support for writing to disk, support for writing to the wire. And internally within Google, everyone just speaks about protocol buffers. If you want to negotiate an interface with another team, you go and negotiate the set of proto buffers you're going to exchange. So as is everything in the Valley, a lot of engineers left Google, went to work for Facebook. And I think, in my opinion, the first kind of few years of Facebook was re-implementing Google. So Facebook came out with a thing called Thrift. Thrift is basically an open source version of protocol buffers and Stubby. It's in use, it's part of the Apache project now. It's in use by Cassandra, Hadoop, HBase, all of the big Java Apache projects use Thrift. And then finally, jump forward, Google releases gRPC. So gRPC is Google's reimagination of Stubby. It still uses protocol buffers, but instead of using the binary transport that Stubby uses internally, which is really highly coupled to Google's authentication system and Google's service discovery system, they use HTTP2 as the transportation layer, so they've all the nice goodness of streaming and so on, and they use protocol buffers as the message format. So, HTTP2. Who here's familiar with HTTP2? Yeah? It's, I guess, a few years old now. It was originally based on something called Speedy, which was a Google Chrome specific format for doing HTTP. And they evolved it into an open standard called HTTP2. And the nice thing about HTTP2 is instead of a TCP connection per request, with perhaps some pipelining and perhaps some kind of persistent connections, you had a single TCP connection and you interleaved requests onto that connection. So it has all sorts of great support for flow control, and because you've got this single connection, you can now do bidirectional streaming. So the server can push you artifacts and you can push messages to the server as well. HTTP2 is a binary protocol, unlike the original HTTP2, which is a text-based protocol. Like you can telnet into a server and type get/HTTP 1.0. You can't do that with HTTP2. But it gives you the ability to do things like header compression. You can do things like multiplexing onto a single connection. You can do much lower latency because you've got these persistent connections. You don't have to set up the SSL tunnels and so on. And it basically allows the web to get a lot quicker. There was a little demo. You've probably seen this already, but oh no, don't want to show that. If you click here, it gives you this cool little demo. So, if we do a refresh, that's loading on HTTP 1, took about 1.53 seconds. Run the same test on HTTP 2, 0.3 seconds. So this is obviously a heavily contrived test because they've split this image up into like 1,000 smaller images, tried to load them all in parallel. But in a real-world example, you might think, imagine I've got a rich web client and it's doing multiple RPCs to the server simultaneously. In modern browsers, there's a limit on how many outstanding RPCs you can have. HTTP2 doesn't have such a limit. That allows you to fetch these images simultaneously. So, one more time. Yeah, pretty cool. So, back to the presentation. So that's the underlying thing. gRPC is HTTP2 with proto-buffer encoded messages on top. There's 3 distinct implementations of gRPC. The first one is written in C and has bindings to all of these different languages. Second one, my favorite one, written in Go. Go gets its own special implementation because Go is special. And the third one is Java. This is based on Netty with boring SSL support and so on. So when you run your gRPC compiler, you get bindings for all of these different languages. It also supports, I've only listed Java once, but it also supports Android's breed of Java. And these are just an example of some of the companies that have adopted gRPC. Cockroach Labs produce a database called CockroachDB, which is an open source re-implementation of Spanner, I guess, which is Google's internal database. I think there was a talk about it yesterday. CoreOS are one of the Kubernetes companies. They use gRPC, massively. etcd is probably one of their biggest projects that use gRPC, and etcd v3 now uses gRPC for its entire interface. I don't know where Docker use it, but I've been told they use it. Obviously, Google. But Netflix, Prometheus is the project I work on. The new Prometheus 2.0 has gRPC interfaces in it. Squared, we've worked obviously as well. Right then, I'm going to sit down and do some coding. Let's look at the example. I'll mirror my screen. Somehow. I'll mirror it with system preferences. Okay. So here's that example I showed you earlier. First I'm going to show you how to compile the proto into the Golang bindings. So I've wrapped it up as a nice make file, but it will show you the command. So quick. You basically run proto-c, the proto compiler. You tell it I want to use gRPC, and you tell it you want it to output in Go. And so if we have a look, I'll give you it in the editor. You then end up with, this file called hello.pb.go. This is the generated bindings for Go for that proto I just showed you. So some boring imports, but you can see it starts defining the structures in Go, so the hello request structure with lots of tags and everything, and starts doing callbacks so that you can register types, and so you can make a client for this, and then so you can make a server for this. Okay. So once we've done that, you want to implement the server. The server implementation is trivial. That's it there. That's all you have to do to implement a server in gRPC. You basically create a structure. This is Go, so it's kind of like an object class, I guess. And you say, I'm going to implement hello, takes a context, takes a request, returns a reply, and I'm just returning the reply, which is hello plus name. Super simple. There's some boilerplate, as usual, as there is in all languages, which is creating a listener, registering your new server you've just created with the gRPC library, and starting that server. But that is literally all the boilerplate you need. Feel free to ask questions during this if you like. So the client is equally simple. You don't have to implement anything for the client. You just go new greeter client. You make a connection, and then you can do, on that client, you can do say hello, pass a request, and then I print the response. So who suspects this will work? If I do make again, that's just built a binary called greeter. If I run it for help, you can see it can be run as a server or a client, and I can give it some addresses, but luckily I can just leave them as default. One's already running. Quit that. In this repository, there's also a version of this implemented in JSON HTTP if you want to compare and contrast. Anyway, so let's run the server. Mode server. That's running. And now let's run the client, because the default mode is client. I don't have to specify that. Tom. Yeah, it works. And just to prove that this is not completely fake, let's do some live coding on stage. So let's do if in.name equals Dave. I hate coding when people are watching. Why did I volunteer to do this? Can't let you do that, Dave. Okay. Recompile the server. Run it again. Tom, that's good. Dave, there we go. Can't let you do that, Dave. Hopefully we all got the reference. So that's hopefully just a quick example of how easy it is to do gRPC clients and servers. All of this code's on my GitHub, Tom Wilkie /gRPC example, if you want to check it out, including the JSON HTTP example, which wasn't contrived, is real. And here's all the encoding and decoding you have to do. Great. Get rid of that. I'll go back to Mirror so I can have my speaker notes. So, now that we're all experts in gRPC, we can get to the real stuff, the real nitty-gritty, scratching the surface. First, I want to talk about how, well, you noticed the title of the talk was gRPC and Kubernetes, and so far I haven't said anything about Kubernetes. So this bit is actually going to be about how I've used gRPC to build microservice-oriented architectures on Kubernetes and the problems I've encountered. So for those who aren't familiar, Kubernetes has this base concept of a pod. A pod's a collection of containers. And normally you would represent your microservice as a set of replicated pods. So you might have, in this example, 6 pods, and you want to use a service abstraction to do the load balancing amongst your pods. So from your client pod, or whatever this happens to be, your other service that wants to connect to service B, it would connect to a virtual IP address, which is enforced by this thing called the kube proxy, and then the kube proxy would route that randomly to a different pod that represents service B. Now, the way this kube proxy does this is it programs the IP tables in the Linux kernel. So kube proxy runs on every single machine. It monitors the API server so it can understand what pods are members of which service. And then when you get an incoming connection on the virtual IP address, it goes and installs a route effectively into IP tables to say route this connection to this pod. Now, if everyone followed that, you'll realize that when you've got persistent connections, if you've got a dumb client library that goes and connects and makes a persistent connection, then every subsequent request will also go to the same pod. And if you do this, then you don't get very good load balancing, right? So you effectively get the client does a connection to do a request, it gets routed to one of these pods, then all subsequent requests go to the same pod, which is kind of dumb. Also, this whole virtual IP address and IP table stuff is a bit complicated and a bit hard to debug. If in your logs you've got these IP addresses that aren't actually matched to a real pod, and you've got to dive into IP tables and the kube proxy's logs to figure out who was talking to whom. So there's this thing called kuberesolver. Kuberesolver is a library that you install in your application, and instead of the gRPC client talking to the virtual IP address, it talks to the API server itself, gets a list of the pods that back this service itself, and just then goes and talks directly to those pods. And it will set up persistent connections to as many pods as it needs to. It'll do its own client-side load balancing. So there's not an argument here. It doesn't save a hop, because the kube proxy load balancing is done by the kernel, so it's super fast. But what it does do, it means in your logs you have real pod IP addresses. It also means you get real load balancing, and you can have your persistent connections. So when we did this at Weaveworks, we saw quite a big improvement on the performance of our services. So we could use these persistent connections in the back end. We got much better load balancing, so the load on our back-end services was much more even. And yeah, it made a big improvement. This is the 4 lines of code you need to set this up, well 3, because there's a new line in there. You create a new kube resolver, you tell it to connect to the service on the given port, and then you create some, oh, I haven't used that. So you really do only need 3 lines of code. And then you basically pass the balancer you get back when you do a gRPC dial, and then everything else is easy. So that's kube resolver, that's the first thing we learned. Second thing we learned, not all of our requests within Weaveworks were gRPC. We still had to speak HTTP at the front end, and this is kind of common. So we came up with this thing called HTTP over gRPC. HTTP with persistent connections was suffering all the same problems as gRPC with persistent connections. The load balancing was particularly poor. And because in the architecture we had, load balancing was more important than connection setup time, we basically just disabled persistent connections. So every single RPC was going over its own connection. It's kind of dumb, right? So we came up with this system, HTTP over gRPC. In our front-end reverse proxy, the thing that exposes the HTTP API, we would read the textual HTTP request and encode it in a proto. Just the raw HTTP request would be stuck in a proto. That proto would then be sent to the backends over gRPC using kube resolver. And those backends would then take the request apart out of the proto, put it back into a standard kind of HTTP request that Go understands, and then run it through the HTTP mux. So it could, these services effectively were just the same as implementing a HTTP service, and this was transparent. The benefits of this approach were A, you get better load balancing. You get the same kube resolver, round robin, randomized load balancing. You can also use persistent connections, so each RPC doesn't have this connection setup time. The big reason we did it like this, so in a traditional architecture, what you would do is you would encode logic in here that says, well, for this endpoint, this HTTP endpoint, I understand what I mean, and I'm going to write this specific protocol, this specific protobuffer out and send it to this specific service. And so this is a lot of logic to sit in the central service that really maps between these two worlds of HTTP and proto-gRPC. We didn't want to maintain that, and we didn't want that to be the single kind of bottleneck for launching a new service and so on. So this nice generic system meant this doesn't have to understand the backend services. It doesn't have to understand what they do. It doesn't have to understand how, how they encode their URLs and what format goes inside the URLs. It's super simple. This is the proto definition for gRPC. You can see a HTTP request has a method, a URL, some headers and a body, just as you would expect. Similarly, the response. When we deployed this, the code's all open source. When we deployed this, we saw, because we got rid of this per connection overhead this per RPC overhead, we saw like almost a 30 millisecond improvement in our 50th percentile latency. So that's a huge improvement for such a small change. So yeah, that's HTTP over gRPC. The next thing I want to talk about is middleware. So you're probably all familiar with middleware from a HTTP point of view. Normally you'll inject some logging, some tracing, maybe some metrics. Well, you can do that with gRPC as well. Super simple. You create, because of some weirdness in the library, you have to create a middleware which wraps all your middleware. And then you can put in some logging middleware. You can put in, this one is instrumentation for Prometheus. This one is open tracing. If any of you have used open tracing, it's absolutely awesome. And then again, where you do a new server, you just pass in the middleware into the server. Now, the benefits of doing this are you can get really consistent logging and instrumentation and tracing across all of your services in multiple different languages just by using the same middleware in each server. It also means like you don't have to write, in every server-side method, you don't have to write, oh, I've got to make sure I log at the top and make sure I export some metrics. And then you can build nice pretty dashboards with this. This is from my company. Every service uses the same middleware. And you can see we export exactly the same metrics, latency and QPS metrics for every single service, which we can then build these nice pretty dashboards and help us respond to incidents much quicker. And one of the things, so I come from an SRE world, I come from a DevOps world. I write code, but I also spend a lot of time operating it. And one of the things, the biggest pattern for making that easy is by making everything look the same. If you can sit down and make all your services export the same metrics, the same logs, the same RPC system, then suddenly when you've got to respond to an incident, you don't have to remember, oh, well, this special service here I did slightly differently. You can just treat everything the same and your incident response becomes much, much quicker. This is the trick that Google use. So advanced topics, I won't have time, unfortunately, because I've kind of only got 10 minutes left and I want to leave for questions. There's a lot going on in the gRPC world. It's pretty new, but it's pretty exciting. So I haven't covered gRPC streaming, the client-side and server-side push. There's loads of really good tutorials on there. I kind of wanted to give you an example of what it's like to operate a service running gRPC instead. gRPC streaming is probably the biggest differentiator for gRPC. It's one of those things that gets really hard to do with vanilla HTTP. You have to go into the whole world of WebSockets and, yeah, horrible. One of the problems a lot of people run into is error propagation. gRPC is very opinionated about the errors you can return, and so there's a very short list of errors you can return. And for a lot of applications, you want to return a bit more information. You might want to return, you know, a stack trace perhaps would be nice. So there's a blog post that I should be publishing in the next couple of days about how to actually propagate custom protos with your error message. It makes a huge difference. Distributed tracing, I briefly mentioned this, but gRPC natively supports distributed tracing. And distributed tracing is the single tool, if you use like Zipkin or Jaeger or whatever the popular distributed tracing frameworks are nowadays, that's the single tool that helped me track down long-tail latency issues in our cluster. You know, it's really hard to debug long-tail latency issues if you can't visualize the request and you can't see the services it went through and where it took its time. So distributed tracing, it's a whole, you could spend an hour just talking about distributed tracing. gogoproto, this is particularly cool. Not a lot of people know that the generated code for proto buffers in Go doesn't actually generate the serialization and deserialization. Go relies on reflection to do serialization. It's the same way it does serialization for JSON and for, you know, all the other formats. It relies on reflection. And now, if any of you, most of you should know that reflection's dog slow. And so the proto buffer serialization and deserialization in Go is also not as performant as it could be. Now these chaps, I don't know, I've never met them, I don't know where they come from, but they've published on GitHub a library called gogoproto, which does generate the serialization and deserialization code and is orders of magnitude faster. And it also allows you some really interesting hooks. So you can do things like you can hook in and do zero copy on your strings and stuff. And when we were implementing our hosted version of Prometheus, Prometheus involves a lot of really small strings when you're sending these label value pairs about and everything. So this made such a huge difference. We managed to take our long tail latency from, oh, I can't remember exactly, but it was like 100 milliseconds down to 25 milliseconds. It was like a 4x improvement in latency at the 99th percentile. It was huge. So gogoproto, if you have any like performance critical gRPC Go issues, I'd really recommend you look at those guys. There's loads of really good tutorials on how to do authentication. Underneath, it's just HTTP, so all of the same rules apply. So it doesn't really worth going into it. And timeouts. gRPC has fantastic support for timeouts. So the last thing, Istio, and there's Envoy and other things like this. This is a new kind of fashion in building these microservice-oriented applications where you have this thing called a service mesh. So this would be a sidecar or ambassador that you sit on every single machine or next to every service. And your service just talks to the ambassador, and then the ambassador then goes and talks to other services for you. So this gives you some nice advantages like being able to do transparent re-encoding, but also you can sit in and you can dynamically alter the traffic flows and drain and give traffic to other services and instrument and generally just more dynamically control the routing of the traffic through your microservice architecture. So I don't use it yet. I just thought it was worth a mention because it's kind of new and exciting. Cool. Thanks very much, guys. Is there any questions?